Imagine the terror of the ground beginning to tremble beneath your feet. Buildings sway, the familiar landscape contorts, and a deep, guttural roar emanates from the very planet itself. Now add to that primordially frightening scene another layer of profound strangeness. The sky above you begins to glow, not with the familiar light of dawn or the comforting twinkle of stars, but with an eerie, otherworldly luminescence. For centuries, across countless cultures and continents, people have reported seeing these strange lights in the moments just before, during, or immediately after a powerful earthquake. These tales were often relegated to the realms of folklore and myth, dismissed by the scientific community as mere panic-induced hallucinations or misinterpretations of more mundane events. These phenomena, now known as earthquake lights or EQLs, represent one of the most fascinating and elusive mysteries in geoscience. They are a bridge between the solid, crystalline world beneath our feet and the gaseous, dynamic atmosphere above our heads. How could the grinding and tearing of rock deep within the Earth's crust possibly manifest as a silent, colorful light show in the sky? The question is a profound one, touching upon the fundamental forces that govern our planet. It forces us to reconsider the Earth not just as a lump of inert rock, but as a vast, electrically active system, capable of producing wonders that defy our everyday experience and challenge our understanding of the natural world. The journey to comprehend these lights has been a long and difficult one, fraught with skepticism and a frustrating scarcity of evidence. For a very long time, the only data we had were anecdotal accounts, passed down through generations or recorded in ancient texts by observers who lacked the scientific framework to explain what they were witnessing. They described pillars of fire, glowing clouds, and spectral flashes that accompanied the devastation of an earthquake. But without photographs, without instrumental readings, these stories remained just that, stories. It was a classic scientific problem, a phenomenon so rare and unpredictable that it seemed impossible to study with any degree of rigor or certainty. Yet, over the past century, the weight of evidence has slowly but surely shifted. The advent of photography and later video recording provided the first tantalizing, tangible proof that these lights were real. CCTV cameras, security systems, and even the ubiquitous smartphone have inadvertently become scientific instruments, capturing these fleeting displays from around the globe. This growing mountain of visual data has forced science to take a much closer look, to move beyond dismissal and begin the serious work of formulating and testing theories. The story of earthquake lights is the story of how a phenomenon can transition from the mists of legend into the bright, clear light of scientific inquiry. So, what exactly do these enigmatic earthquake lights look like? The answer is surprisingly varied, a celestial menagerie of shapes and colors that seems to defy simple categorization. Unlike lightning, which follows a predictable, jagged path for a split second, EQLs can linger, hover, and drift. They have been described as steady, diffuse glows, almost like a localized aurora borealis, painting the entire horizon with swathes of green, blue, or white light. These luminous bands can appear to hang silently in the atmosphere for seconds or even minutes, a profoundly unsettling sight in the moments before the ground begins to violently shake, adding a surreal and spectral quality to the impending disaster. In other instances, the lights are more defined and mobile. Observers have reported seeing distinct orbs or globes of light, sometimes appearing in clusters. These spheres of light, which can be yellow, purple, or even a brilliant pink, have been seen rising from the ground, hovering stationary in mid-air, or zipping through the sky along river valleys or fault lines. Imagine looking out your window during a tremor and seeing not a flash, but a silent glowing ball of purple light drifting past. This is the reality for some witnesses, and these accounts of mobile orbs of light are some of the most baffling and intriguing aspects of the entire EQL phenomenon, challenging our conventional understanding of atmospheric physics. The displays can also be far more dramatic and flame-like in their appearance. Ancient historians, such as Callisthenes, writing in 373 BC Greece, spoke of immense columns of flame that erupted from the ground before an earthquake devastated the cities of Helike and Bura. More modern accounts, such as those from the 2009 L'Aquila earthquake in Italy, describe flames of light flickering just a few feet above the cobblestone streets. These are not true fires in the sense of combustion. There is no smoke, and they do not burn what they touch. Instead, they appear to be a form of luminous plasma, a glowing manifestation of energy released from the earth itself, taking on the terrifying appearance of fire. Finally, some earthquake lights take the form of rapid, brilliant flashes, more akin to conventional lightning but with distinct differences. They are often described as sheet lightning that illuminates the whole sky from an unseen source near the ground, or as powerful blue flashes captured on security cameras at the exact moment of the strongest seismic shaking. These flashes are often associated with the main shock of the earthquake itself and are thought to be a direct and immediate consequence of the immense stresses being released. From silent, hovering auroras to flickering ground-level flames and instantaneous sky-filling flashes, the sheer diversity of earthquake lights is a crucial clue, suggesting that multiple physical mechanisms may be at play. The leading scientific explanation for many of these strange lights transforms our view of the very rocks beneath us. Proposed and championed by physicist Friedemann Freund at the NASA Ames Research Center, this theory suggests that under the right conditions, certain types of rock can behave like enormous electrical batteries. It all begins deep within the Earth's crust. The rocks there, particularly igneous and metamorphic types like basalt and gabbro, aren't perfect inert solids. Their crystalline structures contain flaws, specifically something called peroxybonds, pairs of oxygen atoms that have a negative charge. In their normal state, these bonds are stable and locked within the mineral lattice. When a tectonic plate begins to shift, it places these rocks under immense and rapidly increasing stress. This is not a gentle squeeze, it is a force powerful enough to fracture continents. According to the theory, this intense stress is the key that unlocks the stored electrical potential. The stress waves traveling through the rock break apart those dormant peroxybonds. When they break, they release mobile, positively charged entities known as positive holes or p-holes. These are not physical particles in the traditional sense, but rather vacancies in the electron structure of the rock that behave like a positive charge. The rock, once electrically neutral, now has a vast number of mobile charge carriers flowing through it. These positive holes have a remarkable ability to travel. They can flow together, forming a cloud of charge that surges through the rock from the depths towards the surface. This isn't a slow trickle. The charge carriers can move at incredible speeds, up to 200 meters per second, creating what Freund describes as a solid-state plasma within the rock. This plasma-like state allows the electrical charge generated deep in the hypocenter of an impending earthquake to travel tens of kilometers to the surface in a matter of minutes or seconds. The rock itself effectively becomes a massive, high-speed conduit for a powerful electrical current, a planetary-scale circuit being activated by tectonic forces. When this huge cloud of positive charge reaches the Earth's surface, it doesn't just stop. It erupts into the atmosphere. The surface of the ground develops an incredibly strong positive electric field, which then rips electrons from the air molecules above it. This process, known as ionization, excites the air molecules, primarily nitrogen and oxygen, and when those molecules return to their normal state, they release that excess energy in the form of light. The specific colors observed, the blues, greens, and reds, depend on which gases in the atmosphere are being ionized. In this view, the beautiful, terrifying glow of an earthquake light is the final visible expression of immense mechanical stress being converted into electrical energy deep within the Earth. While the charge carrier theory provides a compelling electrical explanation, it is not the only contender in the scientific arena seeking to explain the mystery of earthquake lights. An alternative hypothesis shifts the focus from solid-state physics to geochemistry, suggesting that the lights are caused by the release of deep Earth gases. The idea is that the immense stress on the crust before and during an earthquake doesn't just fracture rock, it also opens up fissures and cracks that can reach deep into the Earth. These pathways act as conduits, allowing gases that are normally trapped under immense pressure far below the surface to rapidly ascend and vent into the atmosphere. The primary gas implicated in this theory is radon, a radioactive element that is produced by the natural decay of uranium found in rocks and soil. It is well established that radon concentrations in groundwater and soil gas can spike before seismic activity, as new cracks allow the gas to escape more freely. The theory posits that as large quantities of radon are released into the atmosphere, its radioactive decay could ionize the surrounding air molecules. This ionization process, similar in its final step to the electrical theory, would cause the air to glow. Other gases, like methane, are also considered potential contributors to this effect, possibly creating luminous phenomena through chemical reactions in the atmosphere. This gas-centric model, explored by researchers like Japanese seismologist Yuji Enomoto, attempts to link observed lights directly to physiochemical changes measured within fault zones. Proponents of this idea point to the fact that many EQL sightings occur along river valleys and geological faults, which are natural pathways for gas to escape. The appearance of flames flickering above the ground, for example, could be more easily explained by the venting and interaction of a combustible gas like methane with the air, rather than a purely electrical plasma phenomenon. It provides a different mechanism for delivering energy from the crust to the atmosphere, one based on the transport of matter rather than the flow of charge. However, the gas hypothesis also faces its own set of challenges. While radon levels do fluctuate, it is unclear whether enough of the gas could be released over a short period to create the large-scale, brilliant light displays that are sometimes reported. The energy density required for a bright aurora-like glow is immense, and it's a matter of debate whether radioactive decay alone could supply it. It is also quite possible that the truth does not lie with one single theory, and the Earth is a complex system, and the varied appearances of earthquake lights may indicate that different mechanisms are at work in different geological settings, or perhaps that both electrical processes and gas emissions work in concert to produce these spectacular and mysterious glows. The story of earthquake lights is not a new one. It is woven into the fabric of human history, with accounts stretching back millennia. One of the earliest and most dramatic records comes from ancient Greece, in the year 373 BC. The historian Callisthenes, and later the Roman writer Seneca, chronicled the events preceding the catastrophic earthquake that submerged the coastal cities of Helike and Bora. They wrote of immense columns of flame and vast rearing billows of fire that appeared in the days leading up to the disaster. For centuries, such accounts were treated as poetic exaggeration, but in the context of modern EQL research, they now read like a remarkably prescient observation of a powerful pre-seismic light display. Jumping forward nearly 2 millennia, we find one of the most pivotal moments in the study of EQLs in Japan. During a long series of earthquakes that shook the Matsushiro region in 1965, a local dentist and amateur photographer named Dr. Kuribayashi managed to do what no one had done before. He captured the first widely accepted photographs of earthquake lights. His images showed the sky illuminated by a strange aurora-like glow, a mix of blue-white light tinged with red. These photographs, taken during a well-documented earthquake swarm, provided the first concrete, objective evidence that these lights were a real, physical phenomenon, moving them from the realm of anecdote into the world of scientific fact. China, a country frequently beset by powerful earthquakes, also has a long history of EQL sightings. Perhaps the most harrowing account comes from the night before the devastating 1976 Tangshan earthquake. a magnitude 7.8 event that claimed hundreds of thousands of lives. In the hours before the main shock, numerous survivors reported seeing the sky light up with brilliant, multicolored flashes. Some described great fireballs moving across the sky, while others witnessed a sheet of light that turned the night as bright as day. These widespread and consistent reports from a population about to be struck by disaster stand as a chilling testament to the scale of the energy being unleashed. Canada has also been the site of several well-documented EQL events. In 1973, just before the Cross Sound earthquake, which was felt in the Yukon, a man named Jim Conacher was able to photograph several mysterious yellow orbs of light hanging in the sky. This added to the growing photographic portfolio of the phenomenon. Then, in 1988, the Saguenay earthquake in Quebec produced some of the most spectacular and widely observed lights to date. People along the St. Lawrence River reported seeing globes of bright purple-pink light for more than 10 minutes before the earthquake struck, providing an unusually long and clear observation of pre-seismic activity that captivated the public and scientific community alike. The 1988 Saguenay earthquake in Quebec deserves special attention because it became a watershed moment for earthquake light research. The event was only a moderate magnitude 5.9, but it occurred in a populated area and produced exceptionally vivid and long-lasting lights. Eyewitnesses described seeing large, bright globes of purple and pink light moving along the Saguenay River Valley an entire 11 minutes before the main shock. The sheer number of credible witnesses, combined with the unusual color and behavior of the lights, made it impossible to dismiss. It was a clear, unambiguous signal that something extraordinary was happening in the environment leading up to the seismic rupture. This event was scientifically significant because the earthquake occurred in a region of ancient, stable continental crust, specifically within a geological feature known as a graben. This setting fit perfectly with the charge carrier theory proposed by Friedemann Freund, which predicts that such lights are most likely to occur in areas with igneous and metamorphic rocks capable of generating and conducting electrical charges. The Saguenay event provided a real-world case study that seemed to validate the core tenets of the electrical hypothesis. The lights appeared over a specific geological feature, were observed before the quake, and had an appearance consistent with atmospheric plasma, invigorating research in this direction. For decades, however, researchers still lacked the ultimate smoking gun, a video recording of earthquake lights that was perfectly synchronized with instrumental seismic data. This crucial piece of the puzzle finally fell into place in 2007 during a massive magnitude 8.0 earthquake in Pisco, Peru. A security camera in the city captured clear footage of the night sky being lit up by a series of brilliant repeating blue flashes. The flashes were not random. They occurred at the precise moments that the secondary, or S waves from the earthquake, were passing through the ground beneath the camera. This was the first unequivocal video evidence that directly tied the luminous phenomenon to the passage of seismic waves. The Pisco video was a game-changer. It eliminated any lingering doubt that these flashes were caused by mundane sources, like exploding transformers or arcing power lines, as the flashes were widespread and synchronized with the ground shaking recorded by a nearby seismometer, not with power grid failures. This direct temporal correlation provided powerful support for the idea that the mechanical energy of the earthquake itself was being converted into electromagnetic energy. The Pisco footage became a cornerstone of modern earthquake light studies, offering a clear, recordable example of the phenomenon that could be analyzed frame by frame and compared directly with geophysical data, validating decades of eyewitness accounts. In the age of social media and ubiquitous camera phones, sightings of earthquake lights have become more frequent and are shared globally in an instant. This has been both a blessing and a curse for researchers. In September 2017, a powerful magnitude 8.1 earthquake struck off the coast of Mexico, and videos quickly flooded the internet, showing eerie green and blue smears of light painting the night sky over Mexico City. Similarly, during the 2016 Kaikoura earthquake in Wellington, New Zealand, residents were awestruck as the sky turned a brilliant aquamarine colour. And more recently, in September 2023, cameras captured an ominous white-bluish tinge that lit up the sky over Morocco, just moments before a devastating earthquake struck the region. These modern events have provided a wealth of new visual data, showcasing earthquake lights in a variety of geological settings and from different types of earthquakes. Each new video adds another data point, helping scientists to map where and when these lights are most likely to occur. A comprehensive 2014 study that analyzed 65 well-documented earthquake light events since the 17th century found some interesting patterns. It revealed that 97% of these lights are associated with subvertical faults that are nearly straight up and down, even though these types of faults only account for about 5% of global seismic activity. This specificity strongly suggests that the local geology and the mechanics of the fault rupture are critical ingredients. However, the viral nature of these videos has also led to a great deal of misinformation. After a major earthquake, the internet is often flooded with fake or misidentified videos. Clips of exploding electrical transformers, arcing power lines, or even distant lightning storms are frequently mislabeled and shared as genuine earthquake lights. This creates a significant challenge for scientists and the public alike, as it becomes difficult to separate the real, rare phenomenon from the more common and mundane electrical failures that often accompany a powerful tremor. Careful, expert analysis is required to verify the authenticity of each claim and ensure that the scientific data pool remains uncontaminated by false positives. This flood of information also highlights a common misconception about the light's appearance. While many people now associate earthquake lights with the dramatic flashes seen in viral videos, it's important to remember the full spectrum of their manifestations. The slow, glowing orbs seen in Quebec, or the aurora-like bands photographed in Japan, are just as much a part of the phenomenon as the bright flashes in Peru. The increased visibility of earthquake lights in the digital age is invaluable, but it also requires a discerning eye. It pushes researchers to not only analyze the genuine videos, but also to educate the public on how to distinguish these rare natural wonders from the more prosaic consequences of a shaking world. Despite the growing body of evidence, earthquake lights remain one of the most challenging natural phenomena for scientists to study systematically. The primary reason for this difficulty is their profound rarity. A 2014 analysis by Freund and Theriot found that earthquake lights are observed in less than 0.5% of all recorded earthquakes globally. This means that for every 200 earthquakes that occur, only one might produce these lights. This makes them incredibly difficult to predict and even harder to prepare for. Scientists cannot simply set up their instruments in a location and wait for the light show to begin. The odds are overwhelmingly against them. Furthermore, the conditions required to generate earthquake lights are impossible to replicate in a laboratory setting. The leading theory suggests that the process begins with the stressing of hundreds or even thousands of cubic kilometers of rock deep within the Earth's crust. No laboratory press or machine on Earth can come close to simulating the continent-scale forces and vast volumes involved in a tectonic rupture. Scientists can stress small rock samples and have indeed managed to generate tiny electrical currents and faint light emissions, providing proof of concept. However, scaling up these results to explain a sky-filling aurora or a 10-minute display of glowing orbs remains a significant theoretical leap. The unpredictable and fleeting nature of the lights themselves adds another layer of difficulty. They often appear just seconds or minutes before an earthquake, a time when people are understandably focused on their immediate safety rather than scientific observation. Even when they are captured on camera, the recordings are often incidental, a security camera running in the background or a quick shaky video from a smartphone. These are not ideal scientific instruments. They lack the spectroscopic data needed to analyze the chemical composition of the glowing gas or the precise photometric measurements needed to determine the energy output. We are left trying to piece together a complex physical puzzle using chance observations. Because of this rarity and unpredictability, institutions like the United States Geological Survey are very cautious about the phenomenon and state that earthquake lights are not a reliable tool for earthquake prediction. While some lights do appear before an earthquake, many appear during or after, and most earthquakes have no lights at all. There is no consistent pattern that would allow authorities to issue a warning based on a light sighting. A glowing sky could be an earthquake light, but it could also be something else entirely. Until we can understand the precise conditions that create them and can monitor those conditions in real time, earthquake lights will remain a fascinating but impractical indicator of impending seismic doom. From the immense columns of flame described by ancient Greeks to the viral videos of glowing skies over modern cities, earthquake lights have journeyed from the fringes of mythology to become an accepted, albeit poorly understood, scientific reality. We now know that these are not the panicked imaginings of terrified witnesses or the spirits of the underworld. They are a real, physical phenomenon born from the immense power of our own planet. The slow accumulation of photographic, video, and eyewitness evidence has built an undeniable case. Under certain specific conditions, the Earth can and does light up its own sky. The quest to explain these lights has led us deep into the heart of matter, forcing us to see solid rock not as an inert substance but as a dynamic electrical system. The leading theory, which posits that intense tectonic stress can break chemical bonds and release a torrent of electrical charge, is a testament to the interconnectedness of geological and atmospheric science. It paints a picture of the Earth's crust acting as a giant generator, converting raw mechanical force into an ethereal, luminous display. While other theories, such as the release of deep Earth gases, remain plausible, the fundamental conclusion is the same. The Earth has mechanisms to transfer energy from its depths to the sky in the form of light. Yet for all our progress, a deep sense of mystery remains. We must always remember the sheer rarity of this phenomenon. For every earthquake that produces these lights, hundreds do not. This makes them an object of scientific fascination rather than a practical tool for public safety. The dream of a reliable earthquake prediction system based on watching the skies remains for now firmly in the realm of science fiction. The conditions required are too specific, the occurrences too sporadic, and the potential for misinterpretation too high to be used as a dependable warning sign for the millions of people living in seismically active zones. Ultimately, earthquake lights serve as a profound reminder that we live on a world of wonders that we are only just beginning to comprehend. They are a rare and beautiful spectacle, a fleeting glimpse into the colossal forces that are constantly shaping our planet beneath our feet. They show us that even in the 21st century, there are still fundamental mysteries about our own world waiting to be solved. They are a call to curiosity, urging us to keep observing, keep questioning, and keep looking up at the sky, because we never know what secrets the Earth might choose to reveal next in a silent, spectacular flash of light.